Good morning everyone. In the next 20 minutes, I will try to give an overview of what I accomplished in these 3 years of PhD. And I can safely say that my main topic of research in these 3 years was multimedia for cultural heritage. And being in Italy for this kind of topic is it's just a blast, just because if you can see in this map that Italy is one of the very few nations in the world with more than 40 heritage sites as acknowledged by UNESCO. And well, you know that we are just surrounded by a great amount of artistic artworks, and so we have paintings, we have sculptures, we have great architectures, and I think that the role of technology in this context is just very important, just fundamental, not only for the process of preservation, digital preservation as they call, but also for the process of exploitation and valorization of this kind of culture. For example, I can mention the work by Google, which has been recently proposed. It's called Art Project, and it uses the Street View technology used on maps to provide virtual tours into museums. So you can go, for example, in the Museum of Modern Art in New York. You can see the Starry Night by Van Gogh. That's one of my favorites. So you can see the picture, you can see all the information about the picture itself, and well, at this point one could say, okay, that's nice, quite nice, but it's not like the real thing. Well, it's true generally, but with the real thing you cannot do something like this, for example. And this incredible amount of detail, as well as all the other incredible things you can do with the digital version of these artworks, is just an opportunity that should not be wasted in any way. There's one other form of arts in particular in which this kind of gap between artwork and users is just irritating, which is illuminated manuscripts. And Italy has a huge illuminated manuscript that just stands somewhere in the middle between books and paintings. And they are just very rich of illustration, as you can see, but you cannot flip through pages, you cannot touch them because they are closed on glass boxes, so users cannot interact with them. Italy has a huge collection of these manuscripts, and Modena in particular have one of the most important of them, which is the Holy Bible of Borso d'Este, which is really beautiful. And basically, the work of my PhD was to study from these pages, in particular from the digitalized versions of these pages, which provided by Franco Cosimo Panini, and apply some image processing, machine learning magic on them in order to extract all the meaningful contents. Then I applied some multimedia tasks on these illustrations, and I enclosed all this functionality into an appealing user interface. And from the user interface, I deployed it into a multi-touch media station, which is not very clear. Anyway, so I will. That's what it's all about in this presentation. I will subdivide this presentation into 4 main topics. The first one, pre-processing, then segmentation, then the retrieval, and finally some insights about the user interface. So let's start with the image preprocessing, which is quite easy, at least conceptually. It starts from not-so thresholding, followed by connected component labeling, and then a small blob removal, followed by a fluid filling. So we have this kind of mask, and despite it's quite simple from the conceptual point of view, it allows us to remove up to the 80% of pixels of the images. So it's very important because we have high resolution images, so the more pixels we have, the more heavy and demanding the algorithm is. In particular, among these three phases, the most demanding from the computational point of view is the second one, which is the connected component labeling, because we have a lot of thousands of labels for each page to process. So we came out with a very fast algorithm for connected component labeling, Basically, this kind of algorithm is belong to a class of algorithm which actually evaluates the value of the current pixel based on the value of the neighboring ones. And so the optimization of the memory access is just a fundamental rule to improve the performance of the algorithm itself. So basically, we came out with this algorithm, which is actually the most performant connected component labeling on literature right now. And it starts from modeling of the connected component labeling as a decision problem. Then the resulting decision table is converted to an optimal decision tree, and finally the decision tree back to straight C++ code. You are, I think, all familiar with the concept of decision table. In particular, you use the decision table with an AND logic, so you perform all the actions corresponding to a particular set of conditions becoming true. And in this case, we propose another kind of decision table, which we call OR decision tables, in which we can perform any of the equivalent actions, because they create the same results in terms of connected components, but with different computational times. So okay, and that's the first innovation of this proposal. The second one was an automatic algorithm to convert from the OR decision table to the decision tree, and this algorithm is based on dynamic programming and as a formal proof of optimality. And the detail of this algorithm is not available in this presentation for actually time reasons. Anyway, just a primer on the labeling. So when we perform connected component labeling, as typically we perform a raster scan of the image, we have a mask of the current pixel and the neighboring ones, and at each step we just assign a provisional label to all foreground pixels of the image, and we have an online resolution of label equivalencies that is kept updated during the raster scan, and then finally there is a second pass of the image to assign the final labels. And this algorithm, as I described briefly, is just the state of the art of connected component labeling up to 2007. Okay, so this is the mask we used. So 4 pixels, 5 conditions, the 4 neighboring pixels and the current one. We have 3 kinds of actions that we can perform, which is no action at all, an assignment, or a merge between 2 or 3 labels. But if you take a look to this image, you can notice that in a situation like this one on the left, for example, we can perform 3 kinds of equivalent actions. We can assign the label of P, or we can assign the label of Q, or we can assign the merge of the labels of P and Q. But eventually, at the end of the algorithm, all these 3 pixels will share the same label because they actually are 8 connected. So among these 3 equivalent actions, the idea is to choose all the actions which are more cheaper to execute. So in this case, the assignment. So starting from the original decision table, we can perform just a compression of the rules and form this kind of OR decision table. And from this table, we can create the optimal decision tree. And that's the state of the art of connected component labeling up to 2008, but derived automatically and not manually, as authors did in their paper. The question, okay, these are just the results. As you can see, just the optimization of the memory accesses gather significant performance improvement over the previous state-of-the-art technique. Can you go even faster than that? Well, the answer is just yes, because if you look at 2 times 2 blocks of pixels, every foreground pixel in this block is just 8 connected with each other. So eventually, at the end of the algorithm, they all share the same label. And so we can just expand the mask to 16 pixels. So we have 16 conditions and a total action of up to 4 possible actions, and we came out with a much more complicated decision tree and a much more complicated decision table and a much more complicated decision tree. But if you look at the results, you can say that our proposal just blow away the previous state of the art. We performed just 30% faster than the previous state of the art among a set of very different data sets, from synthetic to real ones, and at different resolutions, from the standard resolution up to the highest one. So very good results, and we are quite proud about that. So we have done with the pre-processing. Let's move to the segmentation, in particular the text and pixel segmentation. I will not speak very much about the text segmentation because in the view of our application is not very important. I will talk instead about the picture segmentation, which is based on a block-based analysis. We extract color and texture features from each block. We perform also a limp sheet embedding to reduce the dimensionality of the feature vector in order to easy up the computation. And finally, we just treat the segmentation problem as a classification problem. So as usual, negative samples and positive samples, and let the support vector machine do their job. And we came out with this kind of results. So once we've finished with the picture segmentation, we obtain this amount of, we have more or less 2,800 pictures inside this book. At this point, we can move to the retrieval step, and I would like to start this part, which is maybe the most interesting, with two citations coming from this paper by Elgamal, in which authors just suggest that modern multimedia system needs to interact with users. So it's not only a technical reason due to the limitation of today's technology of content analysis, but it's also a problem of personalization. So the user expects that the multimedia system just provides some personalized users, some personalized results based on the user's needs. And this is actually the schema, very general, of how multimedia system behaves generally. So we have a company or organization which cares about the addition of ontologies, documents, knowledge, and segmentation whatsoever about on the system. And there is the user, which is only a viewer, typically a viewer of the system. It's just the same behavior of Google, which just pre-computes all the distances and lets the user only use the results he provides. And for this project, I would like to define something more different, something more similar to this kind of image, in which the users are just at the center of the multimedia experience, and different kind of users with different kind of expertise can add their unique value to the application. And so experts and curators could, for example, add some commentaries, very expert commentaries, or researchers can add text to the pictures and so on. And in this way, they all contribute with the same kind of system, the same kind of user interface. They all contribute to the same, to improve the quality of the system itself. Let's talk about something more deep in the technical deep. So the visual similarity, which is a fundamental functionality for this kind of system, is based on this kind of feature, which is the covariance matrix, very effective yet very compact descriptors, which encloses all the variance and correlation of a small set of very simple features. They have a problem. They do not lie on a Euclidean space, so they lie on a Riemannian manifold, so the math underneath is pretty more complex. More or less, these are the formulation used for the visual similarity. So the first formulation is just a feature vector, so normalized position of pixels, color channels, and gradients over x and y. The second one is just the construction of covariance matrix itself, which it's a 7x7 matrix in this case. And the third one is just the metric, the distance metric between two covariance matrix lying on a Riemannian manifold, which is called geodesic distance. And these are the results measured as mean average precision, which is a quite strict measure of performance of multimedia system. As you can see, the covariance matrix behave very well, and mostly it behaves very better than the back-and-forth approach, which is considered in literature the more advanced, more successful approach for content-based image retrieval. So up to now we have the ranking of the result presented to the user, and now we want that the user could express their opinion about the results. So it could say what is good or what is bad, which results are good or which are bad, and that is the so-called relevance feedback. And we start from the proposal called mean shift feature space warping to provide this kind of functionality, which has two steps. The first one, the query point movement. We move the query point near to the positive feedback as given by the user, and then the feature space warping, which just warp the space, just modify the space in order to changing according to the user's intentions. And as you could notice from the formulation I've just provided, we need some vector space properties to create this kind of transformation, and these vector space properties are not available, not completely, at least, on the Riemannian manifold. So we have to perform a sort of mapping of the points laying on the manifold up to an Euclidean space which is tangent to the manifold at a particular point, which is, in our case, the query point. So we use this two formulation to perform the mapping from and to the Riemannian manifold, and we use this formulation to make a new proposal for relevance feedback that we called query remapping feature space warping, in which we perform the query points, and then we just remap all the points back to the original Riemannian manifold, and then we create a new Euclidean space tangent to the new query points. And this kind of this intermediate step allows us to improve the quality of representation of the mapping from the Euclidean to the from the Riemannian to the Euclidean. And if you look to this result, you can see how this new proposal just improved the performance of the previous algorithm. So I finished with the technical part. And I will speak a bit, talk about user interface. I hope that's could see something. This is the user interface I provided. There is a preview bar on the top when you can you can use to scroll all the pages of the Bible. When you click on a page, you can see the page on main resolution and the commentary on the left. You can zoom on the pages. This is quite simple functionality, but has gathered a lot of attention because it's very cool to see all the tiny details of these pages. Obviously, you can also change the selections automatically provided in the previous section too, and you can also extract all the pictures available in that page and in this component called dashboard, in which you can just manage all the pictures quite freely, and dragging the picture in the bottom box, you can trigger the visual similarity. So you have all these similar pictures, and at this point you can drag all the good ones on the right and the bad ones on the left to perform in a very easy and a very user-friendly way the relevance feedback, which is a complex functionality, technically speaking. And you can, in this way, refine all the search based on the user's intentions. You can also jump from a page to another. That's a quite nice way to discover new content on this Bible. And also you can add some text to the pictures. You can just add them manually with the keyboard, or you can select from a list of suggestions provided by the system. And these tags are used by a component which is called Tag Navigator, which allows actually to perform textual search, so you can filter out all the pages of the Bible based on this kind of tags. So for example, if you want to now concentrate on all the pages which contains the word Abram, you can do it in this kind of component. There's one final functionality which is called visual assisted tagging, so you can just collect all the, you can exploit the visual similarity in a relevance feedback to collect all the pictures sharing the same kind of content, and then perform a cumulative tagging of all these pictures, which is a very easy way to create this kind of, to improve this kind of, to do this kind of functionality. Just a couple of frames about the real thing working. And it's a pretty complex application because you are seeing something like 13,000 of lines of code, and we have a lot of work to do, but up to now the results are quite good. And the next. I've quite finished, and in the next slides I would like to let you know the success of this kind of application all around Europe. We started from this application just has been the final outcome of a project made in collaboration with Panini, Franco Cosimo Panini. It's called Rerum Novarum, which is the Latin for would be of new things. And it has been presented officially at the Biblioteca Estensa Universitaria this September 24th of 2010, and we have a lot of interested by people, librarians and visitors, because it has been left available to the users to the visitors of the library for entire week. A lot of interest of children who like very much to play with this thing. And then the media station was moved to Frankfurt, the book fair of Frankfurt, which is one of the most, I think, the most important book fair in the world. And then from Frankfurt, it has been moved to Barcelona for the NEM Summit, which is a summit showcase actually organized and sponsored by European Union, and with a lot of sponsorship by a lot of great companies in Europe. And finally, it has been brought back in Italy at Florence for the SCM Multimedia, which is the most important conference of multimedia worldwide. A lot of good feedbacks here from the scientific point of view this time, and a lot of interest. And finally, we are quite excited about the last travel. Will be to Rome this 3 of March 2011, not 10. And it will be presented to this series of events organized by the Italian Ministry of Cultural Heritage, and so we are pretty excited about that. So these are my publication lists and for conferences and journals. I hope that the third line of this journal will be become black soon, because it will be the last part of my PhD. So it will be a very nice to have three journals for these 3 steps of my activity. So thank you very much.